Good. I'd like to thank you all for joining us for this afternoon session titled System in a Package and 3D Devices. So we just have the one paper for this session, so short and sweet, but it's a really interesting talk. I want to thank Dr. Herminso Gómez for providing that presentation for us. He is an X-ray Quality Solutions Manager at ZEISS. He holds a PhD in Optical Science and Engineering at the University of North Carolina at Charlotte, and has authored more than 50 peer-reviewed articles and conference papers. He has over 10 years of experience in the field of X-ray microscopy and industrial computed tomography, and is an active member of several professional associations that promote the advancement in engineering and applied physics. So help me welcome him to the floor.
Thank you, Joe, for the kind introduction. Let's get started. Let me just try to, I need to use this mouse because there is no clicker. So let's try, okay, no? Okay, right. So quick outline. I'm going just to do a quick introduction to the main technique and give you some examples. Then I will talk about how to use artificial intelligence to analyze data with 3D data from X-ray image acquisition. I will give you some more examples so it is clear to you. And I talk about two possible approaches to do image acquisition with artificial intelligence. And then the last topic is how to use this with other correlative workflows from failure analysis, including electron microscopy, and some conclusions and a time for question and answers. So I'm going to start by explaining a little bit of the different techniques of X-ray computed tomography and X-ray microscopy. The classical approach to do X-ray computed tomography is to use a simple setup that is consistent of a flat panel detector, an X-ray source, and a place where you will put your sample, which is going to rotate to collect a set of projections and then create a 3D reconstruction. A little more modified approach and a little more advanced approach will be to use X-ray microscopy, which adds a set of lenses that will give you an optical magnification. The first approach that you see here leverages the magnification, the resolution on geometrical magnification. This one is going to give you a combination between geometric magnification and optical magnification, and that's how you will get a little bit extra resolution. Plus, you will have the ability to switch between all of those different lenses to target different field of views with different resolution, and that's why we call X-ray microscope. It has a set of lenses that you can switch, such as you do in a light microscope. And to give you a quick example, let's think about a smartphone. You can scan the full smartphone and then target fields of view, like let's say a circuit board inside of the smartphone, and check for any type of failure that you are looking for, porosity, and if you like to target a different field of view at a higher resolution, you just switch the lens, go, and now you can check very clearly the porosity in the different VGAs and the connection of the vias between the different layers in this package. If you now like to go to a different region of the smartphone, you could do so, and if you want to target now the camera lens assembly, you could do so, and now check at a higher resolution all the structure of the assembly of this camera lens. And typical measurements are the gaps between the lenses, the thickness of the lenses, which is very important for getting high quality images from those camera devices. And as a last example from this device, I'm going to show the scan of a portion of a battery after being cycled from multiple cycles of charging and discharging. So you can see some of the degradation of the particles inside of the battery to the point that you see some delamination. I need to go forward. Sorry about that. So a summary of the workflow is right here. And as you can see, we have the principal setup, which include the optical magnification. You collect a series of radiographs, basically 2D radiographs, and you collect a bunch of them. It's typical to collect over 1,000, 2,000 projections, and then you create the 3D reconstructions. Once you have the 3D reconstruction, then you can do virtual slicing. So you don't have to do the physical slicing that you will have to normally do to see what is inside with a knife. You basically use a 3D software to do the slicing and see the high resolution, the internal details of this PCB or electronic device. Now, the question is, why do we need to do 3D? Why it's not sufficient to do just a radiograph? And a lot of people still use a radiograph. So I put this little picture there, and I have a question for you. What does that image corresponds to? Any guesses? Is it a hand? Is it a cactus, maybe? A turkey? A jester hat? Well, it's a bunny. Trying to be funny. So the 2D approach can be misleading. And that's why when you go to 3D reconstruction, you really are sure. And I'm showing here some examples here. You see, this is a 2D radiograph. And if you look at this DGA, you can see some kind of low density features, which you could think they are void or porosity, but you're not quite sure. I mean, there are very expert people that try to tilt the sample and try to do some statistical analysis on that. But when you really need to know the root cause of the failure, then you go to 3D and do the 2D slicing. And now you can be sure of what is inside of that device. And that's, you can apply this to any PCB and check all the components that are inside. I'm just showing this as a quick example to check micro bumps, fatigue cracks, hair on pillow, trace of electromigration, broken vias, or any trace of cracks in the layers of the device. This can be applied to any kind of electronics that go into mobile devices like smartphones or laptops, but also to inspect batteries that go inside of those devices, that power those devices. One of the challenges that you have with the electronic devices is that they generally come in a flat form. And that's challenging because when you have a flat device and it rotates, when it goes to this direction and the X-rays need to penetrate through a longer path, then you have a difference in contrast to when it goes through the thinner side of the sample. And what we do is we use a high aspect ratio tomography, so we take more data along the long path as compared to the thin path. And that way we compensate for some of those artifacts that you might see in the 3D reconstruction. Again, this can be applied to any electronic devices that go into mobile devices that we use every day, but also in the automotive. Automotive is growing really fast with the new energy vehicles, which not only has a lot of advancements in batteries, but also in electronics for automotive. So this is one of the type of examples for the different elements that go inside. Okay, so that's how the technique works and can be applied. Now I'm going to switch my presentation to how can we apply artificial intelligence, more specifically deep learning, to improve the data. And I'm going to split this part in two, which it's one set of improving the reconstruction and another for a larger field of view. But let me first be sure that we understand where we are applying these deep learning algorithms. Because a lot of people do deep learning as a post-processing component. And what we are doing here is a little bit different because we are doing it before we go into the reconstruction. So the deep learning is happening between the 2D radiographs and the 3D reconstruction to improve the data. So what we are doing, instead of using the standard analytical reconstruction that has been created from the 1980s or so, we use deep learning to create the reconstruction between the 2D projection stack and the 3D reconstructed data. What is happening with the deep learning network is we are teaching the algorithm to identify noise from features, from actual data that you care about. And once you have that model, then we can apply that to similar type of samples that you are going to be scanning. And here are some of the examples. This is one of those batteries that I showed before. You see what you get with a standard type of reconstruction. And yes, we might be exaggerating a little bit in terms of the number of projections, but it's a very long scan. This is the traditional way of reconstructing with this standard back projection. If you try to put the projections to speed up the collection of data, then you will have a problem. The data becomes noisier. And that's because there is a phenomenon that is happening when you do that is called aliasing. You get aliasing artifacts, basically undersampling. If you now use the deep learning reconstruction algorithm, because it learns where the noise is, it can get rid of it and actually bring back the data. So you get data faster with less number of projections. And that's how we're speeding up the reconstruction of the data. That was a very long scan. There are scans that are a little shorter, and this is the example of the camera device. You see here that this one took 90 minutes to collect with the standard reconstruction, and if we try to put the projections to 120 and scan with 9 minutes, you see a lot of artifacts that hinder what is inside of the data, especially the reconstruction of the surfaces in this device, which is very important for dimensional metrology. If you do now the deep learning reconstruction, then we will have this type of data in 9 minutes and with only hundreds of projections. We don't need to do any more thousands of projections. We can go down to hundreds, and in this case we got a 10x throughput improvement. Okay, now I'm gonna go to a different modality. So that's how you can speed the reconstruction, but there is another challenge that is very classical when you try to scan flat samples or very large samples, and it's the compromise between the field of view and the resolution. The classical approach will be to start targeting a small field of view and collect a set of high resolution scans, but that will prove too long because you have to do this multiple times. Now if you use deep learning approach, you could take a zoom in high resolution in a small field of view and take a low resolution in a large field of view and then apply deep learning to recover the resolution data that you are looking for in the full field of view. So now you combine high resolution and field of view. And I'm going to just show you here another battery example. Now this is a solid state battery. It's a zero charge battery, and it's very tiny, but when you try to get the high resolution data, you have the compromise between a large field of view and the resolution that you desire. What you see here is a 5 millimeters voxel size full field of view, let's call it low resolution data, and a high resolution data collected at 1 micrometer voxel size. And you can see that when you have that high resolution data, then you can see the features more clearly in terms of if you're looking for any type of defects, you can see more defects and the morphology of those. Now if you combine the two, the low resolution data, and use the deep learning training with the high resolution data, and now it applied to the full field of view, then you will get a set of data which is like this. This is reconstructed with deep learning algorithms. So what you have here is you have recovered some of the resolution features in a larger field of view with less data. You don't have to collect a bunch of small field of view and then stitch them to get the full field of view at a good enough resolution. And when you do this with deep learning, then you will see more features and how they differentiate, let's say, in the top of the battery, and if you go down, how they are different from what is in the bottom. And this is a good example to see how you use deep learning to collect the full field of view at a higher resolution. Here you have a comparison of the low resolution data, high resolution, and what you get when you apply deep learning using the high resolution data as a training, starting to create the model. So this is a little bit of a summary of that section. There are two ways in which we are doing deep learning reconstruction. One, to maintain the speed and image quality for interior imaging. And the second one is achieve high resolution in a large field of view. So you recover data by combining a high resolution set of data with a low resolution and now expand to a field of view. Full field of view, a larger field of view. Okay, so this is what you can do with X-rays, and those are very great advancements. And now there are other ways to continue doing the failure analysis. Let's say you start with a fault insulation and you apply any of these methods, including X-ray, and you might find the failure, you might not. If you need to isolate where the section of the sample is, you could go down to nanoscale 3D X-ray tomography, which was mentioned in a talk that was given a couple of days before. And if you're still not happy with that, you can do, now that you know where is the section isolated of the device, where you can now do some cross-sectioning, and then you can go down the route of using FEM or SEM or any type of technique that you know is a way higher resolution that X-ray could give to you. And this is one example of what you can do when you start with a 3D X-ray data, and then you go down the route of isolating the root cause and then take SEM. No X-ray equipment is going to beat the SEM resolution, but of course the main advantage of X-rays is non-destructive. And you're not shooting in the dark. You know where you have to go, and then if you want to do extra analysis, then you do it. So as conclusions, I show you here a series of techniques. We started with explaining the difference between computed tomography, 3D X-ray microscopy, when you have a multi-objective detector, and how you can use high aspect ratio tomography. Then, now how can you integrate deep learning algorithms for two things: speeding the reconstruction of the data at high resolution, and also to expand the field of view. Then we went into a little bit, didn't talk a lot over that, because we've seen a lot of talks about that already during the conference, but you could go to nanoscale tomography and do correlative workflows with electron microscopy. And with this, I will be happy to answer any questions. Just raise your hand.